Welcome to the channel. So today we are pulling back the curtain on large language models and revealing all their real secrets. So no magic tricks, just the science and the math behind it all. So in this tutorial, we are diving deep. I walk you through the low-level matrix calculations that drive transformers, so you can finally see what's really happening inside. So we'll discover how the self-attention mechanism completely transformed the AI world and made today's generative models possible. So the tutorial is split into three clear parts. First, we cover the theory fundamentals so you can understand the principle at work. Then we'll build a Python script using Keras, TensorFlow to train your own text generation model from scratch, step by step, even if you have never done it before. Finally, we'll analyze the generated text together to see what your model has learned and understand its strengths and its limitations. To get the most out of this tutorial, you will need some basic knowledge of Python, linear algebra, and matrix calculation. So you will find a link below to the complete code on GitHub, along with a Jupyter notebook that explains every step so you can follow along and run everything yourself. So by the end, you will finally get how an LLM works, not just the big picture, but all the details under the hood. I know the system can seem overwhelmingly complex, but I've done everything I can to make each concept simple and accessible, even if you are new to the field. So if you are curious about how AI can write, create, and sometimes make hilarious mistakes, this is the video for you. So stick around and let's get started together. So it's crucial to understand that modern AI systems, including transformers, aren't just reasoning entities, they are magical or deeply complex algorithms intentionally programmed with human-like intelligence. Instead, they are sophisticated statistical models trained on vast amounts of text data. At their core, their operation is fundamentally simple, predicting the next word based on learned statistical patterns. Today, impressive generative AI systems which can produce seamlessly intelligent and nuanced text are ultimately performing advanced yet straightforward statistical prediction, word by word. So imagine trying to tell like a complex story by whispering each word to someone who must pass it along word by word. Details quickly fade, context gets distorted, and meaning inevitably gets lost. This was exactly the challenge with traditional text generation methods like statistical models, like Markov chains or n-grams and recurrent neural networks. Markov models predicted the next word solely based on the immediate few preceding words, severely limiting their understanding of broader context. RNNs sought to maintain context through sequential word processing, relying on an internal memory. However, they faced a fundamental limitation, the infamous vanishing gradient problem, where crucial earlier context gradually faded away, hindering coherent text generation. So, the advent of transformer architecture dramatically reshaped this landscape with its revolutionary self-attention mechanism. Rather than sequentially processing each word, transformers allow every word in a sentence to simultaneously and directly attend to every other word. So imagine being in a bustling room where everyone knows everyone's thought and intentions, creating a rich, interconnected understanding without the need for sequential communication. So now let's break down the visual workflow of how generative pre-trained transformer, that we call GPT, perform text generation in detail. So we start with a corpus, with a huge corpus. ChatGPT was trained with the entire internet. In our case, we just have a small corpus. We will see later for the training, we will use some text from Shakespeare, but in this case, it's just this example. So you start with a large corpus. So this dataset contains vast contextual examples, providing rich language patterns. So the corpus is tokenized into sequences of words or subwords, in many cases subwords. And these sequences are prepared for training. The next step is creating input and output pairs. So for text generation, we use what's called an autoregressive approach. So we select a fixed length window, that is sec length, is our variable, we'll see later in the script. for example, can be 100 tokens, that depend on the specific case, and slide it across the text corpus, okay, creating overlapping input and output pairs. So as you can see here, it's just the offset is just one word. Each sequence pair is one training example. So these examples are grouped into batches for efficient parallel processing for GPUs, okay, the batch size. Why we use fixed windows? Transformers actually require consistent input sizes to build the uniform attention matrices. So using sliding windows ensures all sequences have exactly the same length, allowing the attention mechanism where each word simultaneously attends to every other word to function efficiently. So why batch size? Actually, the batch size that is like grouping multiple input and output sequences is crucial because it leverages modern hardware architecture, particularly GPUs. So GPUs are specifically optimized for parallel computations, efficiently handling numerous calculations simultaneously. So by processing multiple sequences at once, it batches training becomes significantly faster and more resource efficient, so greatly accelerating the learning of intricate language patterns. So in short, batching maximizes GPU utilization, speeds up the training process, stabilizes learning through averaged gradients, and ultimately results in quicker convergence for two sophisticated statistical models. The next step is from token, I get the ID, and then the embedding. So words or tokens, in our case, we see words, but in the reality, it's token. So it can be like a sub-words or point or other kind of symbols. From the input sequence are first mapped to a unique integer IDs through a predefined vocabulary. So each integer ID is then transformed into a high-dimensional vector called an embedding using a dedicated embedding layer. So these embeddings are initially randomly initialized, typically drawn from a uniform normal distribution, for every token in the vocabulary. So we create an embedding vector of n dimensions, for instance. Why embeddings? Yeah, because they capture semantic relationship between words, meaning that the words with similar context or meanings end up close to each other in the embedding vector space after training. So initially random, these embeddings gradually refine themselves throughout the training process via stochastic gradient descent, combined with the backpropagation. So adjusting to accurately reflect linguistic patterns found in the data. So during training, after performing a forward pass, that is calculated prediction, we calculate actually the loss, so the difference between predicted and actual values, and propagate this error backward through the model. So this backward pass, we call backpropagation, updates the embedding vectors incrementally, guiding them toward a meaningful semantic relationship. So I just assume that you're already familiar a little bit with how feed-forward operation and backpropagation in neural network work. If you aren't, please check out my other video where I explain these fundamental concepts. So each token in the vocabulary has its own embedding vector composed of n dimensions, and is here, and that we call it embedding, the dimension. So often ranging from hundreds of thousands of elements. For instance, ChatGPT models like GPT-4 typically utilize embeddings with dimension of thousands of elements. That meaning that each token is represented by a 1,000-dimensional vector. So this high dimensionality allows for nuanced representation, capturing subtle semantic and contextual relationship between words, which greatly enhance the model's ability to generate coherent and contextually rich text. After the embedding, we apply the positional encoding. So transformers actually don't inherently understand or recognize the sequential order of words, as they process all words simultaneously through the self-attention mechanism. So to address this critical limitation, transformers utilize a special approach called positional encoding, which explicitly adds positional information to each embedding, ensuring the model recognizes and leverages word order effectively. So we specifically, as you can see here in the picture, we use the sinusoidal functions for positional encoding because they offer several advantages. So the uniqueness, every position within a sequence is represented uniquely, Consistency patterns learned for specific positions during the training generalize seamlessly to sequences of different lengths encountered during inference. Sinusoidal functions naturally extend to positions beyond the maximum length seen in the training, allowing the model to handle very long sequences effectively. Here's the formal representation of positional encoding using sinusoidal functions, where actually POS, POS, is the position of the word within the sequence. I actually denotes the dimension within the embedding vectors, the embedding vector. The model actually is the dimensionality of the embedding. So the sinusoidal patterns alternate between sine and cosine functions. So lower embedding dimensions capture broader positional informations, slowly varying patterns, whereas higher dimensions capture finer details. Ultimately, this explicit encoding approach ensures that transformer effectively understands and differentiates between contexts. After providing tokens into embedding vectors and generating positional encodings, the transformers actually combines these two sources of information through an element-wise summation. Specifically, each token's embedding vector is directly summed element-wise with its corresponding positional encoding vector, resulting in what we call the combined encoding. So, this combined encoding simultaneously encodes both the semantic meaning of words from embeddings and their positional context from positional encoding, so allowing the model to understand both context and word order. The combined encoding has a shape specifically structured as follows, as you can see here, sec_lang, embed_dim, and batch size. As we will see later in the script, I use the same variable. The sec_lang is the number of tokens in each input sequence, as we saw before. The embed_dim is the dimension of each embedding vector. And the batch size, as I explained before, is the number of sequences processed simultaneously, enabling efficient parallel computation on GPUs. So the core innovation of the transformer is the self-attention mechanism, enabling each token in a sequence to dynamically assess the relevance of every other token within the same sequence. To achieve this, the transformer generates three distinct linear projections from the combined embeddings. We have the queries, Q, represent what each token is actively seeking or querying within context. So imagine each token looking around, trying to find related context. We have the keys, that represent actually what each token offers or advertises about its content. So each token signals its relevance to others. And values that carry the actual semantic information that tokens provide, delivered when a token selects another via its query. So linear projection using dense neural network. So as you can see here, we apply a linear projection using dense neural networks with linear activation. So each of these projections, Q, KV, is computed by applying separate dense neural network layers with linear activation directly to the input embeddings. Okay, so the linear operation for each projection, as you can see here, if you know neural networks, can be formally represented as output is the input multiplied for the weights plus the bias. Okay, so as you, because we use linear activations, we don't apply non-linearities. So later we will see we will apply a ReLU, but in this case just linear, and we are just preserving direct interpretability and numerical stability. So the question is, why do we use dense layers with linear activations? So using a dense neural network with linear activation, in this case for Q, K, and V, allows the transformers to learn optimal representation through training without imposing unnecessary constraints. It maintains interpretability, so linear projection make it straightforward to reason about transformation mathematically. Numerical stability, so the linear transformation help to ensure stable gradients during backpropagation, and also flexibility because despite their simplicity, linear transformations still enable the model to learn sophisticated relationships by adapting weights and biases. Just some information about the forward pass and backward pass, actually. During the forward pass, the embeddings are multiplied by weights and biases are added. So specifically, the combined embedding vector in this case, for each token passes through 3 distinct dense layers. As you can see here is Q key V, and the metric X is multiplied for the W matrix, and we add the bias later. So the X is the input embeddings, the W, Q, key V, and the BQ, BK, BV are learned parameters for each projection. So these resulting vectors are then utilized to calculate attention score, determining how strongly each token should attend to every other token. If we talk about backward pass for the training, so during backpropagation, the model computes gradients of a loss function with respect to the parameters WQ, KV, and the biases. So these gradients indicate how each parameter should be adjusted to minimize the loss. So in the backward pass, if the output leads to high error, calculated by the loss function that we will see later on the bottom, for the gradients propagate backward through dense layer. This is the normal behavior of a neural network, and it's going to inform how much each parameter contributes to the error. So we calculate the derivative, and the gradients is going to have this formula. And as you can see here, the derivative of loss. So we have the gradients with respect to weights W and gradients with respect to biases P, 2 different derivatives. So we are going to calculate this with the chain, the derivative chain. So these gradients adjust weights and biases via stochastic gradient descent and or related optimizer, and incrementally, of course, refining the projection until optimal performance is achieved. After this part, we apply an important operation that is called splitting in multi-head attention, as you can see here. Instead of a single attention computation, transformers use multiple attention heads. Each head independently performs self-attention in a different embedding subspace, allowing the model to capture various aspects of relationship like syntactic, semantic, short-term, long-term. After attention computation, results from all heads are concatenated in a single vector. And it's also quite good for the parallel computation because we are going to calculate each head, each dense split in parallel with all the heads together. After this, we are going to apply a dropout. This is a dropout regularization in transformer, and is applied for all the Q key value tensors. So after applying linear projection with dense neural networks to obtain queries, keys, and values, the transformers include a crucial regularization step called dropout. So dropout is applied directly to these tensors before calculating self-attention score. Dropout is a popular network regularization technique that randomly set a fraction of the elements of a tensor to 0 during training. So typically, dropout rates range between 0.1 to 0.3, meaning that 10% or 30% of the values within a tensor are randomly set to 0. So this introduces actually noise into the training process, encouraging the model to become robust and avoid overfitting. So after this step, we are going to enter into the transformer block. And the first step of the transformer block actually is calculating attention scores. So once we have these Q, key, and V matrices, the transformers calculate attention score by performing a dot product, okay, between the queries and the keys. As you can see here, there is a transposition. So we transpose the key and we invert the shape. We are going to have a sec-lang projection dim. As you remember, the projection dim is just the embed dim divided for the num heads. And specifically, for each word, the dot product determines the degree of similarity or compatibility between the query vector of one word and the k vectors of all words in the sequence. So the resulting similarity matrix captures how strongly each word is related to every other word contextually. Higher dot product values mean higher relevance. After this step, there is the scaling step. So to maintain numerical stability to avoid excessive magnitude, which can dominate the training, causing vanishing or exploding gradients in some cases, each score actually is scaled by dividing it by the square root of the embedding dimension, as you can see in this formula. So this step ensures attention scores remain balanced and numerically stable during training. After this, we are going to enter in the softmax transformation. So after scaling, we convert these similarity scores into normalized probabilities using the softmax function. So this transforms raw score into probabilities, clearly showing how much attention each word should pay to every other word. So as you can see here, we convert similarity score into an attention probabilities, and from the previous step, we get this tensor with the shape batch size, numHeads, secLeng, and secLeng. So they are square metrics. Each entry score, okay, bhij, is the similarity between a single token I in batch B and head H and token J in the same batch head. Okay, so then we apply the softmax along the last dimension of that sensor. That's why we apply x is -1. In other words, for each quadruple bhi, the sum of the outputs over the dot equals to 1. Concretely, if you fix batch G, head H, and query position I, the x is -1, means you normalize over all values of J's. Those weights sum 1 across J and indicate how much token I attend to token J, okay? If we consider the diagonal, so in a self-attention matrix, each token pays attention to every other token in the sequence included itself, that is the diagonal. So the self-weight actually tells you how much of my own value do I keep. This will repeat for each head also in this case. After that, we are going to multiply the attention weights with the value matrix. This line performs a batch metric multiplication where each head and each position takes the attention weights, okay, and multiplies them by all corresponding values, effectively computing a weighted sum of those value vectors. And we get at the end an attention output that has a projection dim, secLeng, and batch size. In short, it transforms the per position attention distributions, that is the attention weights, into context-aware embedding by mixing the original value representation according to those attention score. And the next step is the reshape and transpose. That actually we are going to merge the multiple heads. After computing the self-attention across multiple heads, we need to recombine all the heads to form the final output of the attention mechanism. Currently, the tensor of shape, batch size, numHeads, secLeng, and projection dim. After transform, we get the batch size, secLeng, numHeads, and projection dim. We replace actually the secLeng with the numHeads inside them. We reshape and we concatenate the projection dim for all the heads to get back the embedding dimensions, the original embedding dim. So after this, we are going to have a unique tensor, and we get that with these dimensions, secLeng, embed dim, and batch size. After this, we are going to apply another dropout. We apply the residual connection, actually the residual connection add to the original embedding back to the attention output. So we are going to give it back a little more information about the inputs. This ensures actually crucial information that isn't lost. Then layer normalization standardizes the vector to have a stable distribution, significantly helping with the training stability. And after this, we get an output that we are going to enter the feed-forward network, okay, also called FFN. So let's talk about the core idea of this feed-forward network. After the attention mechanism that produces the context-aware embeddings for each token, we still want to transform that information further, just to have the model to reason, combine, and refine meanings in a ways that self-attention maybe alone cannot do. So this is where the feed-forward network comes in. Let's talk about the architecture. So the FFN is applied independently to each token, position-wise, and it identically across all the position. This means that there is no mixing between token position at this stage. The operation focuses on transforming each token internal representation. So the FFN consists of two dense, fully connected layers. The step one is expand the dimension. From the embed dim, we go to FF dim. We are using a ReLU activation. We apply ReLU because it introduces non-linearity, letting the model learn complex functions like logical relationship, composition of meanings, and others. So these layers actually allows the model to interact across dimension within each token, enabling more complex internal transformation. And then we project back to the original dimension. So the high-dimensional hidden vector is then projected back to the original embedding size. So the second projection actually ensures that the tokens vector can be passed along the subsequent transformer layers, maintaining compatibility in shape and preserving consistency across layers. Again, another dropout, residual connection again, and layer normalization are applied for the same reason, improving robustness and training stability like before. So we just explain one transformer block, but as you can see here, we're going to use multiple transformer blocks. And each transformer output is going to be the next input for the next transformers block. So why we are using this stack? Actually, multiple identical transformer blocks are staked sequentially, as you can see here. Each block refines the embedding representation further. So initial blocks capture like maybe simpler linguistic patterns, while deeper blocks progressively understand more complex context, grammar, themes, and styles maybe. And after this, we are going to output the projection. After this step, there is the scaling step. So to maintain numerical stability, to avoid excessive magnitude, which can dominate the training, causing vanishing or exploding gradients in some cases, each score actually is scaled by dividing it by the square root of the embedding dimension, as you can see in this formula. So this step ensures attention scores remain balanced and numerically stable during training. After this, we are going to enter in the softmax transformation. So after scaling, we convert these similarity scores into normalized probabilities using the softmax function. So this transforms raw score into probabilities, clearly showing how much attention each word should pay to every other word. So as you can see here, we convert similarity score into an attention probabilities, and from the previous step, we get this tensor with the shape batch size, numhead, sec-length, and sec-length. So they are square metrics. Each entry score, okay, BHIJ, is the similarity between a single token I in batch B and head H and token J in the same batch head. Okay, so then we apply the softmax along the last dimension of that sensor. That's why we apply axis -1. In other words, for each quadruple BHI, the sum of the outputs over the dot equals to 1. Concretely, if you fix batch G, head H, and query position I, the axis -1 means you normalize over all values of J's. Those weights sum 1 across J and indicate how much token I attend to token J, okay? If we consider the diagonal, so in a self-attention matrix, each token pays attention to every other token in the sequence included itself, that is the diagonal. So the self-weight actually tells you how much of my own value do I keep. This will repeat for each head also in this case. After that, we are going to multiply the attention weights with the value matrix. This line performs a batch metric multiplication where each head and each position takes the attention weights, okay, and multiplies them by all corresponding values, effectively computing a weighted sum of those value vectors. And we get at the end an attention output that has a projection dim, sec-length, and batch size. In short, it transforms the per position attention distributions, that is the attention weights, into context-aware embedding by mixing the original value representation according to those attention score. And the next step is the reshape and transpose. That actually we are going to merge the multiple heads. After computing the self-attention across multiple heads, we need to recombine all the heads to form the final output of the attention mechanism. Currently, the tensor of shape, batch size, num heads, sec-length, and projection dim. After transform, we get the batch size, sec-length, num heads, and projection dim. We replace actually the sec-length with the num heads inside them. We reshape and we concatenate the projection dim for all the heads to get back the embedding dimensions, the original embedding dim. So after this, we are going to have a unique tensor, and we get that with these dimensions, like length, embed dim, and batch size. After this, we are going to apply another dropout. We apply the residual connection. Actually, the residual connection add to the original embedding back to the attention output. So we are going to give it back a little more information about the inputs. This ensures actually crucial information that isn't lost. Then layer normalization standardizes the vector to have a stable distribution, significantly helping with the training stability. And after this, we get an output that we are going to enter the feed-forward network, okay, also called FFN. So let's talk about the core idea of this feed-forward network. After the attention mechanism that produces the context-aware embeddings for each token, we still want to transform that information further, just to have the model to reason, combine, and refine meanings in a ways that self-attention maybe alone cannot do. So this is where the feed-forward network comes in. Let's talk about the architecture. So the FFN is applied independently to each token, position-wise, and it identically across all the position. This means that there is no mixing between token position at this stage. The operation focuses on transforming each token internal representation. So the FFN consists of two dense, fully connected layers. The step one is expand the dimension. From the embed dim, we go to FF dim. We are using a ReLU activation. We apply ReLU because it introduces non-linearity, letting the model learn complex functions like logical relationship, composition of meanings, and others. So these layers actually allows the model to interact across dimension within each token, enabling more complex internal transformation. And then we project back to the original dimension. So the high-dimensional hidden vector is then projected back to the original embedding size. So the second projection actually ensures that the tokens vector can be passed along the subsequent transformer layers, maintaining compatibility in shape and preserving consistency across layers. Again, another dropout, residual connection again, and layer normalization are applied for the same reason, improving robustness and training stability like before. So we just explain one transformer block, but as you can see here, we're going to use multiple transformer blocks. And each transformer output is going to be the next input for the next transformers block. So why we are using this stack? Actually, multiple identical transformer blocks are staked sequentially, as you can see here. Each block refines the embedding representation further. So initial blocks capture like maybe simpler linguistic patterns, while deeper blocks progressively understand more complex context, grammar, themes, and styles maybe. And after this, we are going to output to the projection. Okay, so let's analyze the Python script provided in the repository below. With this script, you will be able to build, train, and visualize a transformer-based neural network for natural language processing tasks. So let's start with our environment setup. So we are importing TensorFlow, Keras, our deep learning framework, NumPy for numerical computations, Matplotlib for visualization, and Visual Keras. In this part, we set up the GPU, so it's crucial for performance. We detect available graphics cards that enable dynamic memory allocation, so TensorFlow grows memory usage as needed rather than hogging on everything up front. So this prevents crashes and allows multiple processes to share GPU resources. Now let's dive into the transformer block that is the heart of our implementation. This is like, as we saw already in the previous visual workflow, this is the sophisticated reading comprehension module that pays attention to important words, processes information, and combines inside with regional step. So we have the multi-head attention here, the layer. We expand dimensionality and add a non-linearity here, compress back to original embedding size, stabilize training after attention, stabilize training after feed forward, prevent overfitting in attention and in feed forward. Okay. In the call function, we have the self-attention. The input attends actually to itself. Residual connection here, plus normalization. And feed-forward processing here. And the final residual connection plus normalization here. As we already saw in the previous workflow, the multi-head attention is like having multiple experts analyze text from different. We move to the complete transformer model architecture here. This combines word embeddings, positional encoding, multiple transformer blocks, and a final prediction layer. Okay, we have this first line here that convert word IDs to dense vector, embedding, add position info, and the final layer predicts next word probabilities here. This is the function positional encoding that apply the sine, here apply the cosine, and in the get angles function actually is to calculate frequency rates, and then multiply the position by the frequency rates. When we call the function, the words become dense vectors in this part. We add the positional information here, the inputs. We process through multiple attention layer in this part, and we convert to vocabulary probabilities in this last part. As the positional encoding actually is crucial because neural network, as we saw, don't understand word order naturally, so we use a sine and cosine to different frequency to create a unique position sequence. Let's look at data preparation with the create free sequences function. It creates actually training sequences by sliding a window across the text. It creates thousands of input and target pairs, where each target is the input shifted by one word. The model learns to predict what comes next at every position. Okay, now we have a really interesting function that is the text generation. This is the core, of the inference to the LLM. ChatGPT works, of course, it's more sophisticated than this is just the basics, but that include every concept that the LLM inference used. We use the autoregressive sampling strategy. It's the actually cornerstone of modern language model inference. This process is fundamentally different from training, as we generate one token at a time in a sequential causal manner. Let's analyze step by step. The phase one is input preprocessing and tensor shape management. So the first critical step involves converting our human-readable text into numerical format our model expects. So the vectorizer starts in NumPy call. It performs several operations under the hood. So the first is text tokenization. It splits the text into discrete tokens, words or subwords. Vocabulary lookup maps each token to its corresponding integer, and the tensor creation, so it wraps all the IDs in an NumPy array with the shape 1 and sec length. So the shapes management logic is crucial for maintaining consistent input dimensions, so our model expects exactly sec length tokens. So we implement intelligent padding and truncation. This is the padding logic, and this is the truncation logic. About the padding, where the input is shorter than sec length, we prepend zeros. So this creates a left padded sequence where the meaningful tokens appear at the end of the sequence, allowing the model to focus on the most recent context for prediction. And about the truncation strategy, when input exceeds the sec length, we take the rightmost token. This preserves actually the most recent context, which is typically most relevant for next token prediction. Phase 2 is the autoregressive generation loop. Actually the heart, we are going to convert in tensor, of course. And the phase 2 is this loop. So the heart of the text generation lies in the autoregressive loop. That is a process that mirrors how humans generate language by considering previous words to predict the next one. So what I'm doing now, for example, talking to you, when I use the next word, my brain always thinks, what I say just right now, which is the last sentences to predict next word. And it's doing exactly like that. Each iteration actually follows a precise sequence. The sequence is that first is the prediction. This single line triggers actually a complex cascade of operation that we saw before in the model. So the first is the embedding lookup. Each token ID is converted to a dense embedding dimensional vector. Second substep is the positional encoding addition. So mathematical sine cosine patterns are added to embed positional information. And after this, we have the multi-layer attention processing, where that each transformer block applies a self-attention mechanism, allowing tokens to attend to relevant part of the sequence. And after, we have the feed-forward processing. Dense layers transform the attendant representation. And at the end, we have the final projection, where last dense layer projects the vocabulary size, producing raw logits for each possible next token. And actually, it's what is going to happen inside the model. So the next substep is logic extraction and causal masking. So this part, as you can see here, this line implements causal masking by selecting only the prediction for the last position in our model architecture. So each position predicts the next token. Okay, so prediction 0, -1 contains the probability distribution over the entire vocabulary for what should come after our current sequence. So the indexing 0, -1. So 0 is the first and only batch element. -1 is last sequence position where we want to predict the next token. And here we have all the vocabulary dimensions. So after this, we apply the temperature, just a mathematical operation. We divide the prediction for temperature. Actually, temperature scaling is a crucial technique for controlling the creativity versus conservatism trade-off in generation. The mathematical foundation is this one, the formula. So is exponential of all the values divided for the sum of the exponential. And we just, when we apply the temperature, we just divide each term for the temperature like this. And what it means actually, it means that, for example, for temperature lower than 1, for example, 0.7, it makes the distribution more peaked, increasing the probability of the most likely tokens. This produces more conservative, predictable text. The temperature is bigger than 1. It flattens the distribution, giving lower probability tokens more chance to be selected. This increases the creativity by risk incurrence. If the temperature is 1, there is no modification. It uses the model's raw learned distribution. The next step is the stochastic sampling with categorical distribution, and this is the line. Actually, it implements multinomial sampling, which is more sophisticated than simply taking the highest probability token, actually. It expands, okay, the themes. It adds actually a batch dimension here, converting the shape from vocab size to one vocab size, okay, as required by the random categorical. At num samples 1, it means that samples 1 token ID according to the probability distribution defined by the temperature scale logits. And why actually not the argmax, like a normal softmax? Direct argmax selection will always pick the most probably token, leading to repetitive deterministic text. So stochastic sampling introduces controlled randomness while still respecting the learned probability distribution. The next step is the context window management and sliding window technique. This part actually, it implements a sliding window approach essential for maintaining computational efficiency. We have the token appending, so the newly generated token is added to our sequence. We have a window sliding. We keep only the most recent sec length tokens, discard older context. This prevents also sequences from growing indefinitely, keeping memory usage constant regardless of generation length. And attention relevance, because the recent tokens typically have more influence on next token prediction than distant. And after this, we convert to tensor. And we have the last step, that is the vocabulary lookup and token to text conversion. We returns actually with the vocabulary, we return the learned word to ID mapping, okay? And if predicted ID this part prevents index errors if the model predicts invalid token IDs. And at the end, we retrieve the actual word token corresponding to ID. So now let's orchestrate everything in the main function. We start by loading we are using a Shakespeare dataset here. We download the complete words from Shakespeare, create a vocabulary of 10,000 most common words, and generate training sequences where each target is the input shifted by one position. The seek length is 100. We also set the vectorizer. It create a word to number, actually this part. This part TextDS actually it wrap the text in dataset. The vectorizer adapt actually this part, learn vocabulary from text, and it convert this part, the entire text, to numbers and create training sequences. This part create training sequences. Okay, it input the sequence here, and it target the sequence in this part. We set other parameters that you already know, embedding, the NumEds, the FFDIM and num layers. And this configuration actually give you about 13 million parameters. Each word gets a 256 number representation. 4 attention heads provide different perspective, and 4 layers create increasingly sophisticated understanding. After that, for training, we set up monitoring and early stopping. We create details log and for monitoring using early stopping to prevent overfitting in this part, and process example in batches for efficiency. Finally, we generate text to evaluate our trained model. Okay, so it's time to test our script and start training the model. Guys, let me say up front that I'm not using GPUs, so the training will be extremely slow, but as this is just for educational purposes. Let's see, for example, how long it takes to train on CPU for this text, assuming 20 epochs, for example. Okay, so I already activate my virtual env in Python, and I just run the script. So this is the text at this link, and you can see it's all Shakespearean text. And as you can see, it's really long, really long. So now we calculate how long it takes to train all this text for 20 epochs. And after, maybe we take just a little part of it and we try to inference on some sentences. Whoa, it takes so long. So almost 1 hour, 50 minutes for each epoch. So I think totally is going to take more than 36 hours. So now you can easily imagine the crazy sheer computational power required to train a large-scale model with the billions of parameters on the entire text corpus of the internet and for multiple epochs. So how many GPUs that does it actually takes to train something like a GPT-4 or something more advanced? Crazy, right? Let's experiment something easier. We try to take just a little part of this text, so at the end we can predict some sentences inside the text. Okay, so let's try with a little part of the corpus that I save here, and it's just really small. So we try to train with this corpus and ask to predict from this part that actually is from this part. We start from the object of our that actually is this sentence here. Let's see what is the response if it outputs something that is similar to this text. Let's try. And here we go. Oh, much smaller, just 16. It's going to be really fast. So let's cut the video. So see you later. So here we go. During training, you could see actually how the loss decreased step by step, and the early stopping actually stopped the process after just 4 steps because the loss was not decreasing enough. And here it is. Let's evaluate the predicted text. So it's saved here, the generated text. This is the original. So we start the with the sentence, the object of our and after our start to predict. This is the original, and this is the prediction. That actually is quite strange. It's quite strange, but it's normal. So we can compare the 200 tokens with the original. We have two examples, 100 and 200. Let's compare these both. Let's find some kind of similar semantic echo, like some similarities in the semantic. For example, there is a theme of lack versus abundance. The original talks about misery, abundance, and sufferance. The generated text throws in words like superfluity. So you can see here superfluity, meaning excess, poor rest, impediment, all hinting at lack and excess. There is also social class and conflict. For example, the original as patricians, revenge gained to them, our pikes, and in the generated one we find also chief, citizen, price, kill. Is something social class and conflict. There is also something about moral or existential language, I think. In the original, there is a God's no, hunger for bread, thirst for revenge. And in the generation, we have heaven. And in the other part, we have a God's no, so it's something of correlation. There is also lexical borrowing. As we know, the generated text copies some vocabulary from the original, such as patricians and citizen. And also the syntax style, actually, the generated text, despite being jumbled, maintains a slightly archaic tone with the phrases like rest especially as and heaven citizen, reminiscent of old texts of Shakespearean phrasing, matching the original style. So what you see here is still just an embryo. The system has only just begun and has barely been trained, but it's already fascinating to watch how it starts to reproduce words, themes, and even a style similar to the original. With more data and training, these models can really improve, as you see with ChatGPT, a lot, and become much more coherent. So this is just the beginning, and the best part is seeing how artificial intelligence slowly comes to life. So thanks to all our viewers for watching, and see you in the next video.